hours around.
All right, we'll go ahead and get started. Go ahead and respond to the attendance poll if you have not done so already. And let's see. All right. We have, so on Wednesday, we started talking about floating point numbers in the computer, because this is how our computer represents numbers, with bits. Okay, so we only have 64 bits to represent a number, which means we cannot represent every value on the number line. We can represent big numbers and small numbers, but certainly not every value, because there's infinitely many of them. And so we have 64 bits. We're looking at the IEEE 754 standard, which says of those 64 bits, 52 are used for the mantissa, 11 are used for the exponent, and 1 bit is used for the sign. Okay? And to kind of illustrate what's happening, we are using a mini float version. All right, let me have you guys settle down, please. And in our mini float version, we have 3 bits for the exponent and 4 bits for the mantissa. Okay, but we will still see kind of the same kind of effects and strange artifacts and weird things that happen in the regular 64-bit version with our mini version. Okay, and so we said the exponents. When we apply it, there's going to be a bias so that we can represent both positive and negative exponents. And so when you have something like this, with 3 bits, our bias happens to be 3. And so if our values are stored like this, our exponent is 101, which turns into 5 in decimal. We apply our bias of 3, so our exponent is 2. If our mantissa is 0111, this turns into, positive 1.0111 times 2 to the 2. And when we do the computation, it comes out to be 5.75. And we said, as far as the mantissa goes, we can always assume that the leading digit is a 1, because that's how scientific notation works, right? We also covered a few special values. We said if the exponent is all 1s and everything else is 0, then that's going to be infinity, positive infinity, or negative infinity. And if the exponent is all 1s and we don't have all 0s in the mantissa, then we get something that's not a number. Okay? And so we'll continue on today to just kind of discuss a little bit more about our about our numbers, and just talk about what happens in our double precision floating point. Okay, so let's just talk about. Okay, so earlier we said 0, 1, 1, 1, 0, 0, 0, 0. This corresponds to positive infinity, all right? So I could ask, what is the largest value we can represent, largest positive value, that is not infinity, okay? And so that would be, what would that be?
1.
So my exponent will be 110, and what will I put in for the mantissa? 1111. Is that good? Okay, so if I do this, my exponent is equal to, what do I have? I got 4 plus 2 plus 0. I have an exponent of 6. We apply the bias of -3. And so my exponent is 3, okay? So if this is my mantissa, then what we have is 1, and then I copy the mantissa over. 1.1111 times 2 to the 3. Okay, so this is binary scientific. Okay, and so I will just roll the point over 3 spots, and I'll get 1, 1, 1, 1.1, and this is 8 plus 4 plus 2 plus 1 plus what? 1/2. Is it okay? And so if I add all of this up, I get 15.5 in decimal. So this is the largest number I can represent that's not infinity, okay? So with mini float, with our mini float, the largest value I can represent that is not infinity is 15.5. Anything bigger than 15.5 will be called infinity, okay? And I know that seems kind of silly because 15.5 doesn't seem like a very big number, right? But this is the largest value that my mini float with 8 bits, okay, used in this floating point representation, this is the largest value I can represent, okay? And largest value I can represent that's not infinity is going to be 15.5. Now, it seems a little bit silly, but with 64 bits, on the computer, we run into the exact same issue, just on a bigger scale, okay? So for 64 bits, you know, in R, we have dot machine $$X max, okay? This is the largest value I can represent that is not infinity, okay? I can say dot machine $$X max, okay? And this is the kind of the biggest number I can represent. This is on the order of 2 to the 1023. Well, that's 2 to the 1023, and if I add 2 to the 1022 and things like that, and if I just say sum 2 raised to the like 1023 down to 1,000 and things like that, okay, we get something quite close to my, hold on, let me just do options, digits equals 7 now, okay. Okay, so, you know, it's something on this order here, okay? Now, if I tried to add something substantial together, like if I tried to do 2 to the 1023, and if I tried to add another thing of 2 to the 1023, so 2 to the 1023 is this, and if I try to add that again, the computer tells me it's infinity, okay? Because it's not able to handle a number bigger than this, okay? Anything bigger than this, the computer is going to say, that's just infinity, okay? And so, so this is on the order of 10 to the 308 power, which is probably big enough for most of our needs, but it's also a far cry from infinity, right? 15.5 is a far cry from infinity, but so is 10 to the 308, okay? So this is, you know, on the order of 1.797 times 10 to the 308, okay? And it's just a little bit smaller than 2 to the 1024. So if I do 2 to the 1024, that will, the computer will error out and tell me it's infinity, okay? So the largest value we can represent is a little bit smaller than 2 to the 1024, okay? And it's this. This is our dot machine double max. Okay, our equivalent in our mini float is 15.5. Okay, that's our dot machine double max mini float max. Okay, is 15.5. Let's just ask, what is the next largest value? Okay, so the next largest value would be 0, 1, 1, 0, and what would I have for the mantissa bits? Okay, and the largest one I had 1, 1, 1, 1, so the next biggest value would have what? 1, 1, 1, 0, yeah? Okay, so my exponent is still 6 minus 3, 3. I still have an exponent of 3. And with this in my mantissa, I have 1.1110 times 2 to the 3, okay? And so I would just roll the point over 3 spots. I have 1111.0, and this becomes 8 plus 4 plus 2 plus 1 plus 0, and we get 15. Okay, so the next largest value is 15. So, if we're counting, we go 15. So it goes ... 15, 15.5, infinity. All right, in our floating point number line, that's what we have. Okay. Earlier I said we can always assume. So one of the rules. So we have a rule that says we can always assume that the leading mantissa digit is 1. Okay. But there's a problem with this rule. Okay, and that is there's no way to represent 0. Okay, and that if I tried to do 0, 0, 0, 0, 0, 0, 0, 0, what would this become? This becomes, my exponent is 0, I apply my bias of -3, and I get -3. And then, and this becomes 1.0000 times 2 to the -3, and this becomes 1/8. Okay, so that's an issue. So we make an exception to our rule. Okay, and the exception is if the exponent bits are all 0, we enter denormalized or subnormalized mode. Subnormal mode. Okay, and what that means is that so if the exponent bits are all 0, okay, our leading mantissa digit is now 0. Okay, and our bias will become 1 less than usual. Okay, and this works for our mini float and also the 64-bit version and everything. Okay, so let's just think, what will our smallest regular normalized value be? Smallest positive normal value. Positive normalized value. Okay, which means Mantissa has lead digit 1. Okay, so the smallest positive normalized value will be 0. What will I have for the exponent? 0, 0, 1. And my mantissa will be all zeros. Okay, this is the smallest positive normalized value I have. So my exponent is going to be what? This is 1. I apply my bias. My exponent is -2. And so here I have 1.0000 times 2 to the -2, which is equal to what? 1/4. Okay. In order to kind of keep things in a continuum with continuity, all right, we modify, so our exponent is 2 to the -2. If we talk about our largest positive denormalized value, okay, so the mantissa has lead digit 0, okay, this will be 0, 0, 0, 0, 1, 1, 1, 1. Okay. And so when we do this, we'll have 0.1111. And in order to kind of, because if we were just kind of counting in binary with 4 binary places behind the point, this would be kind of the biggest number I can have before I get to 1. And so what we're going to do is we want to keep the same exponent. Okay, we keep the same exponent. So our bias is now 1 less than normal. We have a bias of 2. Okay, so our exponent is going to be 0 minus 2 equal to -2. Okay, bias is 1 less than normal. Okay, and so what is this? So this is 1/2 plus 1/4 plus 1/8 plus 1/16 times 2 to the -2, so times 1/4. And this becomes 15/16 times 1/4, 15/64. Okay, so the smallest positive normalized value is going to be this, 1/4. The largest positive denormalized value will have all zeros here and all ones over here, and it will be 15/64. Okay, so very close to 1/4, because 1/4 is 16/64. It's just a tiny bit less than that, 1/64 less than that. Okay, so that's going to be the largest denormalized value that I can have. Okay, what is the smallest positive denormalized value I can have? Okay, so it must be greater than 0. Smallest positive denormalized value will be 0, 0, 0, 0, 0, 0, 0, 1, right? Okay, so my exponent is going to be -2. And then with the mantissa, I'm going to have 0.0001 times 2 to the -2. And so this becomes 1/16 times 1/4, and I get 1/64. Okay, because this is the half, quarters, eighths, and sixteenths. All right, and then thus, you know, 0 would just be 0, 0, 0, 0, 0, 0, 0, which becomes 0.0000 times 2 to the negative 2, 0. Okay, so 0 is 0, all zeros. But again, we'll have a positive and a negative 0. Okay? That's just one of the effects of having a sign bit. We'll have a positive and a negative 0. Is this okay? All right, so I created this little worksheet, okay, to kind of just say, all right, so here's my sign. These are all kind of bits for our mini float. The sign bit, the exponent bit, and the mantissa, okay? So this will just be 0, okay? No surprise there, okay? 0.0000 times 2 to the 0. Or I'm sorry, 2 to the negative 2. Okay, and then so over here, this is the, oh, and I'm sorry, one last thing. This thing that we call, this is our dot machine. Whoa, why is my text? I don't know, just something happened here. Okay. This is our dot machine double X-Men. So this is and then double epsilon, double these are all kind of I don't know. All right, the double X-Men, I think this is the smallest value we can represent, non-zero value we can represent. Okay, let's go back to our thing here. This is our smallest positive denormalized value that we can have, and so this is equivalent to 1/16 times 1/4, and this is 1/64. So we've covered this already, right? So this is what we have. 0.0001 is 1/16. 2 to the negative 2 is 1/4. This is equivalent to 1/64. All right, over here I have what? 0010. This is the next biggest value, okay? And so this is 1/8 times 1/4, and we get, we have 2/64 or 1/32, okay? All right, and then what do we have here? We have 1/8 plus 1/16 times 1/4, and so this becomes 3/64. Is that okay? So I'm just counting, incrementing my bits in my mini floating point to just kind of show. So our step size, what is our step size? Our step size right now is 1/64. Okay. So the largest denormalized value that I'll have is going to be this, which is 1/2 plus 1/4 plus 1/8 plus 1/16. So we have 15/16 times 1/4, and I get 15/64. Step size is still, and the next value, okay, now we're in the normalized zone, okay? And so I have 1 times 2 to the negative 2, 1 times 1/4, and this is equal to 1/4. Right. What do I have here? 1 plus, so my mantissa now has a leading bit digit of 1, and this is 1 plus 1/16, right? Okay, and I'm still multiplying by 1/4, and so this is equal to what? (17/64). Okay, so here my step size is still 1/64. Okay, and so if we think about why my step size is 1/64, okay, what we have is the smallest bit is 1/16, and my exponent is basically 1/4, and so when I do 1/16 times 1/4, I'm getting increments of 1/64. Okay, and so that's what's going on. And so the largest thing that I'll have here is going to be 1 plus 15/16. Okay, so this is still using the same exponent of 2 to the negative 2. I have 1 and 15/16, and I'm multiplying this by 1/4. So what does this equal to? (1 and 15/16). So we can think of this as 16/16. Okay, 16/16 plus 15/16 gives me 31/16. So I'm going to have 31/64. Okay, and then I get to here, and what do I have? I have 1 times 1/2. Okay, and I get 1/2. All right, or 32/64. All right, and this is what I believe to be the beauty of floating point, the floating point number system. What is this next value? Okay, my exponent is 0, 1, 0, which turns into 2 to the negative 1, and my mantissa is 0, 0, 0, 1. So that's going to be 1 plus what? 1 and 1/16 multiplied by what is my exponent? 2 to the negative 1, so this is 1/2. Okay, and what is this equal to? So 1 is 16/16, so I have, what is it? 17/32. Okay, is that all right? I'm not trying to like stump you guys here, okay? And then over here I have 1, and here we can call this 2/16 times 1/2, and this gives me 18/32. Okay, so what is my step size now? My step size is now 1/32. Okay, so up until from 0 to about 1/2, okay, 0 to 1/2, my step sizes were 1/64. Okay, but now that I'm dealing with numbers bigger than 1/2, my step sizes are 1/32. Okay, they've gotten, I have bigger step sizes. Okay, and so I can get to this point, which will be 1 plus 15/16 times 1/2, and what is this equal to? So 16/16, 1 is 16/16 plus 15/16, we're going to have 31/32. Okay. All right, and then what do I have here? So now that this has maxed out to 1, 1, 1, 1, it rolls over to 0, 0, 0, 0, and my exponent rolls up to 0, 1, 1. Okay. So my exponent, after I apply the bias, is 2 to the 0, or 1. Okay. And so I have 1 times 1, and we have 1. Okay. And what do I have here? So I have 1 plus 1/16, okay, times 1. And so I'm going to have 1 and 1/16. Or maybe I'll write 17/16. Okay, if we're okay with this. Okay, and so what is my step size now? Okay, my step size is 1/16. Okay, because basically what's going on is, smallest bit is 1/16, and the exponent is 1/2. So when you multiply those two together, the step size is 1/32. Okay, but now my smallest bit is still is 1/16, and my exponent is 1, so the step size is 1/16. Okay, and then so way later, we're here, and we have 1 plus 14/16 times 8, okay, and this gives me 15. And here I have 1 and 15/16 times 8, and this gives me 15.5. Okay. And so basically right here, my smallest bit is 1/16. The exponent part is 8. Exponent portion is 8, so the step size is 1/2. All right. So what we have are a floating point number line. All right, so I'm going to just write C worksheet for details. But basically, our floating point number line looks something like this. Okay, at least the positive, non-negative side. Okay, so we start off at 0, and then up until 1/4, this is our kind of our denormalized area, and then after beyond that is normalized. And from 0 to 1/2, okay, so in our worksheet, we saw going from 0 all the way up to 1/2, my step size is 1/64. Okay, and then when we went from 1/2 all the way up to 1, my step size is 1/32. Okay, and after 1, my step sizes were 1/16. Right? Okay, and then after 2, basically up to 4, what will the step size be? Will be 1/8, and so on and so forth. Okay, until we get to basically we're at a point where we're at 15 and 15.5 are, from 8 into this, our step is 1/2, right? And then after that, it's just considered infinity. Okay, and so what we see is that for small values, our step size is small. Okay, and for large values, our step size is large. Okay, and this happens, okay, we see an extreme version of this because I only have 8 bits to play with, but the same exact concept happens when we are dealing with 64-bit floating point precision, okay, because we have only 64 bits to work with, and so in order to cover kind of as much of the number line as possible, we give it lots of precision near 0, but as the numbers get bigger and bigger and bigger, our step size gets bigger and bigger and bigger. Okay, and that allows us to kind of cover a lot more of the number line, allowing us to go basically from negative 10 to the 308 power to positive 10 to the 308. Okay, but there's some weird consequences of this. Okay. All right. Well, before I go on, is this okay? This idea of the step size, the increment when we're talking about increasing our bits and stuff, or not increasing our bits, but keeping the bits the same. But as we increase our values, the step size between values gets bigger. Okay. So there are some weird consequences. Or I don't know. Maybe they're not that weird. I think they're kind of weird. All right, what if I run a loop? I say we start off with x equals 1 in the global environment, and then I just do this. It's not while true. X is x plus 1, okay? So it's going to just go x is 1, it adds 1, x is 2, it adds 1, x is 3, and it goes, and we do this, and let's say we just let the computer run for a very long time, okay? So we start this loop, okay, we come back a year later, and we ask computer, what is the value of x? What do you think the computer will say? Okay. X will not be infinity, okay? Okay. Dot machine max is, what is it? It's along, double X max is around this. Do you think it'll be that? What do you think X will be? Any guesses? Okay, X will not be infinity. X will not be machine max. Okay. No. X will run into issues. Okay. So I can start off doing, you know, x is 1, and I can do while true, x is x plus 1, okay? And I can just let this run, and it's not going to reach there in time, okay? But so, you know, I can say like 1 1000, 2 1000, 3 1000, 4 1000, 5 1000. We can just kind of see how far it gets. And all right, and it managed to count all the way up to 376 million. Okay, that's pretty good, right? That's pretty good, but it's a far cry from what we'll encounter. Okay, let me just kind of show you. Let me do options, digits equals 15. Okay, and just kind of see, is it 2 to the 53? Okay. Okay. So I'm going to start off with this very big number. So we're going to say we let the computer run for a very long time, okay? And it's gotten to this point, okay? We come in and we're going to say, all right, computer, how are you doing? All right. So we're going to say D, let's update D and add 1 to it, okay? And I put parentheses around it so that the computer will kind of print out the result. Okay, so we have whatever this is, 900719925474098 blah, 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 0983, okay? I add 1, 84, 85, 86, 87, okay, no surprise here. 88, ending in 88, 89, 90, 91, 92, 92, okay, and we're stuck at 92. This is not anywhere close to double machine X max, okay? We're D is this, and if I say, well, what is D plus 1? It gives me this. What will happen if I do D plus 2? Will it work, or will it still give me the same? It works, okay? And so I can try, okay, so we add 2, and this works, but if I try to do plus 1, that seemed to work, but if I try to add 1, it doesn't work, but if I do plus 2, it seems to work. What happened? What happened was we reached a point on our number line where the step sizes, remember the step sizes started off small and they kept getting bigger and bigger and bigger? We reached a point on our number line where the step sizes were no longer 1, but they became 2, okay? And so the computer is no longer able to differentiate between, you know, this value and 9995, okay? Because we don't have enough bits to keep track of all of that. So adding 1 to this, because our step sizes are now 2, we can't keep track of differences smaller than 2, okay? So we can add 2, okay? Our step size is now 2, and we can keep track of adding 2 to all of these things. And if we kept adding 2 to our thing, it would keep working until it reaches a point in the number line, okay? Our numbers get sufficiently big where the step size becomes 4, okay, and then it can no longer differentiate increases of 2 or not, okay. So so this is kind of a weird thing that happens, right? In that because you know we're accustomed to real numbers always kind of working out for us, but with floating point numbers, the number line is not this smooth, continuous thing, okay? There's real increments between one value and the next value you have it. We have 64 bits, so it seems like it's smooth and continuous, but it's not, okay? And once you get entering this range, you can't even differentiate between integers. You can only, your step sizes are now 2, and later on they'll become step sizes of 4 and 8 and so on and so forth, okay? Basically, the step size is about 2 to the 16. No, what is it? 2 to the. Because we're using 52 bits in the. I'm sorry. Because we're using 52 bits in the Mantissa, the step size is 2 to the negative 52 of whatever value you currently have. Okay, so so we're at 2 to the 53. I guess I can do, you know, 1 or maybe 2 to the, I can't remember. But basically, you know, at this point, once we've reached this, our step size is now 2 at this point, okay? And so, so anyway, that's something I don't think we would have anticipated, okay? But, you know, running this forever, x will not be this, but x will be basically 2 to the 53, okay? 2 2 to the 53, and then it gets stuck. Okay, because the step size on the number line is greater than 1. Okay, so anyway, these are just things that we have to be mindful of and watch out for, okay? We've already showed that you cannot expect exact precision, like 0.1 plus 0.2 does not equal 0.3 because we have binary approximations for all of these things. We run into other strange things like this, where adding a value to a big value might not have any impact, right? So you might say, update this value with some other value. If that value is relatively small compared to the value you're adding it to, it's not even going to change the value at all. And so, so these are things we have to be mindful of when working in floating point numbers and not real actual numbers. Okay, have a great weekend, you guys. We have a holiday this weekend, so we'll see you guys, I guess, on Wednesday.